What I want to start with the history is I want to go back and do an origin story for Landweber flatness, and then later in the lecture I'll tell you what it is after we've done the history, and I want to do some introduction on the development of BP and Morava K theory from the point of view of my work with Doug, because it's his birthday, and then I want to review give a survey of some current work that's being done. So in particular I want to thank the organizers. This is a particularly appropriate conference for Doug because he is the tribe's unofficial eclipse master, and this will be my third eclipse with him because I went up to Rochester to see an annular eclipse with him. So the context of what I want to talk about, going back before many of you were born, is about 50 years ago, Brown and Peterson constructed BP, and it was done to produce a counterexample for something, and it wasn't until Quillen gave a whole bunch of formulas as to how to use it that this was a viable object. Morava has his Columbia preprint around 1970. It's very hard to nail that down because of Jack's quantum theoretical existence. You can't place it in space and time at the same time. But before BP, there was complex Bourdism, and that was made a cohomology and homology theory back in 1961. These are early days for such things. Connor and Floyd wrote their book, very nice book, in 1964. I actually met Connor once in my career. How many of you ever met Connor? You met him, a couple of them, okay. So I was curious about him. He's still alive. He's still around. Back, it used to be that old guys used to go to conferences, and they've completely stopped coming to conferences now, except Brayton Gray showed up and destroyed that joke. But nobody laughed anyway, so it wasn't that good a joke. Doug and I, so talking about ancient history, Doug and I met as first-year graduate students in 1968. We went to the same topology seminar for years together while I was a graduate student. And as first-year graduate students, we heard that we were thinking about the same thing, just the multiplication on S3, the quaternions, and he came over to my apartment to compare notes with me, and he had this beautiful mathematical description of what was going on. And I had this sheet of paper that looked like somebody had had too much of something to smoke and got his hands on crayon. And there might have been a reason for that. At any rate, this meeting eventually, if all my jokes take that time delay, this is going to be a problem, At any rate, this led to 9 papers with Doug, and I'm going to wander through some of them in this talk. Now, this slide is phrased wrong. I don't want to denigrate all of the 1960s and 70s in algebraic topology. It was about the two things that I'm going to talk about. There were hundreds of pages of papers that led up to those two things, and everything else is gone. And that goes back to Connor and Smith. And this is the first thing I want to talk about because it's what leads up to this concept of Landweber flatness. Where does it come from? What's the history of it? They studied the homological dimension of the Bourdism of a space. And here are some of their papers. If you look at that last one up there, it's an IHES paper. It's over 100 pages long. But they had lots of papers on this. They really studied it. And so what is the homological dimension? It's the length of the shortest free resolution. If you take mu stars, it's a polynomial on even degree generators. And you can set it up like this, and n is this smallest number. And that's the homological dimension. Now, Connor and Smith did the groundwork for this, and so I say they have 3 main theorems, but the truth is that groundwork took most of those 100 pages. You had to do a lot of work to set this up. And then they got 3 results out of it. The first was that if you look at the projective homological dimension and it's equal to 0, that means the homology has no torsion. Another way is to say that if it's 0, then it maps to mod p homology is surjective for every prime. So there are two ways to phrase this. Their second theorem was to go up, you know, they're going to do induction, right? So they go up by 1, and the homological dimension is less than or equal to 1 if connected complex K theory has no torsion from the generator of the coefficient ring. And another way to phrase that is that if the Bordism is onto homology, integral homology. So the third one is that the homological dimension is less than or equal to 2. I should have 0, 1, and 2, but I wanted to give them 3 theorems. And that is if the Bordism is onto the connected complex K theory, then you have dimension 2 or less. And there's no torsion-free version for this one. And after this, they were stumped. If you look at the coefficient rings, what they wanted was they'd hoped to get 3 by having a theory that had the first 2 generators, but it just wouldn't work for them. And that's when Dave Johnson came into the picture. He said, do it 1 prime at a time. And he knew my thesis, so instead of MU, we wanted to use BP. And now we have these theories where if you look at BP bracket N, you take the first N generators for BP, and those are the degrees there. And these theories now do what Connor and Smith wanted to do with MU. These work. So if the homological dimension is less than or equal to N, then BP bracket N has no Vn torsion. A rephrase of that is that the BP homology is onto BP bracket N minus 2. So there's dozens of ways to do this, and Dave and I wrote down all of them. Of every different way you could think of doing it, or phrasing it. And in particular, if you take anything above K, you get a surjection. And if you take anything below that, it's not a surjection. So here's the big picture. You have this infinite sequence of maps going all the way down to mod P homology. And if the homological dimension is exactly N, then every one of these things, every one of these maps is a surjection. And every one of these maps after that is not a surjection. So it's a really pretty result that you have all these surjections and then all these non-surjections. If you find anywhere that you get a surjection, then you're done. You know a great deal about this. So we found a complete solution, and having done that, we discovered it wasn't good for anything. But I'm sure you've all been there. So the only thing that survives out of that paper is the so-called Johnson-Wilson theories. And the coefficient ring there is you take the BP bracket ends and you invert Vn. And since this is about Landweber flatness, this is a generic example of a Landweber flat thing. That if you multiply by P, the one characterization of a Landweber flat thing is if you multiply by P, it's injective. And if you then mod out by P and you multiply by V1, it's injective. And then if you mod out by V1, you multiply by V2, it's injective. And in this case, when you multiply by Vn, since it's a unit, it's injective. And when you mod out by Vn, there's nothing left. So this is an example of a Landweber flat object, but I haven't told you what Landweber flat means. So we had different names for these at the time, but we had this theorem that if you have the En homology of a space, you could get it from BP just by tensoring with the coefficient ring. And this started a grudge match with Peter Landweber. And because everything we did depended on one unstable operation. And that is that if you take the zero space of the omega spectrum, the classifying spaces for these cohomology theories, BP bracket N splits off of BP. Now, we actually know the entire homotopy type of all of the spaces in the omega spectrum for BP. But this was all we really needed to prove these theorems. It's one unstable operation. And you note that there were things like this in existence already. If you take CP infinity, it splits off of BU. And in Connor and Floyd's book, they showed that BU split off of MU. And that's why the Connor-Smith theorem worked for the case they could do. Now, we made no use of Landweber's work, which is where the grudge comes in. So he had to go in, and he used his operations to completely reprove all of our useless theorems. Now, except one, because we had an unstable operation, if we had a finite complex, a finite dimensional one, we could get a bound on the homological dimension. And he couldn't do that because he was working completely stably. But in the process of doing this, he proved this familiar theorem. And if you look at that theorem, it looks the same as what we proved, but it isn't. It's an entirely different theorem. Because we had a cohomology theory, or a homology theory, and we showed that it was the same as tensoring with this. He didn't have a homology theory. He had this ring. He had this thing, and he said, well, he didn't say it like this, but he said, that's Landweber flat. And if it's Landweber flat and I tensor with BP, I get a homology theory. So this is entirely different from what we did, and it's the thing that makes his work survive. After all of this stuff, after all the Connor-Smith things that you've never heard of, and all of Dave and my work, and even that paper, you wouldn't want to go back and see him reprove those theorems, but he gets this concept of Landweber flatness, and that's where it comes from. So, and it's still around today. We use it all the time, and that's the origin story there. But it's also the story of sort of how you develop things. You have these backwaters. You do hundreds of pages of papers of theorems and stuff, and they're really pretty theorems, and then what lasts 50 years later is just a little bit of it. So in those days, we were trying to understand BP and Morava K theory. And you guys probably don't know about this, but back in the 70s, when you don't know about it, right? If you gave a topology seminar, you had to spend the first 20 minutes telling people what BP and Morava K theory was. So I think we're past that, or maybe we've gone beyond it and we have to do it again. I'm not sure. Most of the theorems at that time were narcissistic or dead ends. They were just about BP and about Morava K theory, but you also need applications if you're going to have new theories, or there's no point. But you can't have applications if you don't know about BP and Morava K theory, and you have to know that before you can use them. So an example that was talked about both by Haynes and by Mike yesterday is looking at the omega spectrum for Bourdism, for complex cobordism, and BP, but both of them phrased it as we understood the homology. And so we actually did a lot more than that. I look forward to Mike's talk next year when he adds the MU on the left and not just the one on the right. You left that one out. Okay, so I mean, there is no torsion in these spaces, and so the Atiyah-Hertzberg spectral sequence collapses, but you still have formulas from that MU on the left. You have the formal group law there, you have the formal group law there on the right. They interact with each other. You get the universal object that has this one big relation, that has total information. It's utterly useless, but it's total. So we did get early applications following Morava, and if you look in our paper with Haynes and Doug where we introduced the chromatic spectral sequence, you'll see Morava's name several dozen times in the introduction. And this paper brought VN periodicity into homotopy theory, but that wasn't actually the application. That was the application for the next generation. But at the time, that wasn't the application. Where the application was we had computed X2. And what that meant was that if you look at the traditional atom spectral sequence, almost nothing in X1 and X2 survived. And that made the old people pay attention, because that was something they knew about and something they cared about. And we came in and we said, almost all of your favorite elements have differentials on them, and they're done. And so that, whereas VN periodicity, I don't think they cared much about at the time. And now people care about it. So in my view, to develop a theory, you also have to calculate real spaces, the standard spaces in algebraic topology. So BP and Moravec-Cathie are complex orientable, so a lot of the basic spaces are really easy to deal with. But we took on the Eilenberg-MacLane spaces and calculated the Moravec-Cathie theory for all of those. And I think that's turned out to be useful, but at the time it was just fun, narcissistic mathematics. We got another application out of that, though. We got the Connor-Floyd conjecture. And I should point out that we beat Steve Mitchell, who proved the Connor-Floyd conjecture a few months after we did. But even our proof was a decade or two after Connor and Floyd had discovered they had no need for it. So Mike and Doug and I showed that Moravec-Cathie theories just don't see K invariance. Now, you guys take spaces apart using Goodwillie functors and stuff like that, but back in our day, we used Postnikov systems, simple work. But here's the theorem, is if you take a finite Postnikov system and you look at the loops on that thing and take the Moravec-Cathie theory, it looks exactly like if you just took the Eilenberg-MacLane spaces for all of its homotopy groups. So it doesn't see anything about the structure of the space except the homotopy groups, which is sort of an interesting theorem about how useless something might be, but I'm fond of it. So I want to take a little side trip. There are other theories. If you take out these first generators, then you have a new theory. The homotopy is mod P with Vn and Vn plus 1 and so on, like that. And among other things, Doug and I computed this hop ring as well. We took all the spaces in the omega spectrum for that and calculated the Pn homology of that. And that's really obscure. It's probably so obscure, I question whether Doug even remembers it. Maybe is the answer. But in fact, it started something that I think should be better known, but I can prove that it isn't, but I'll get to that proof in a minute. There are other theories, and you should think of these theories as somewhat like BP bracket M in relation to the PNs. So they're much the same as this. These guys split off of BPK for certain K. You pick the N that works, and in our case, with Boardman, we found that these things split off of the PNs for certain K. Now, if you look at these things, these are Zabrodsky spaces where there's no torsion in homology, there's no torsion in homotopy, and now Alex knew that and could prove a structure theorem about them, that for every K there was such a thing, but he didn't know what they were. You could just do it without knowing what they were. So any double torsion-free space is the product of these things. So for every K, there's a K-1 connected space that has no torsion in homotopy or homology, and any space that has that property is the product of such a space. The examples are the spaces in the omega spectrum for BP. And they're all done in terms of these BP bracket ends, so you know the homology, you know the homotopy, you know everything about them. Now, in our case, we can do exactly the same thing, except these spaces now have no Vn torsion in homology and no Vn torsion in homotopy. Now, no Vn torsion in homology is easy to state. You take connected Morava K theory, and you look at that, and you take the Vn, and there's no Vn torsion. And saying what you mean by no Vn torsion in homotopy is a little harder, but basically you build it up the same way you build a Postnikov system, except you build it up with pieces from the omega spectrum from connected Morava K theory, where you only kill off torsion things until you have no torsion left. So for this, so any double torsion-free space, meaning no Vn torsion and no Vn torsion in homotopy or homology, is the product of these things. You pick your N, you pick your K. There is a unique space that has this. It's irreducible. It's very nice. It's all the same sort of theorems. People like the BP bracket N spaces. These have got to be better, because a whole bunch of you guys all look at Kn localization. If I were going to do something like that, and I'm not, I would take these spaces and do Kn localization at them, because they've got to be interesting. Anyway, that was just a sideshow. It was something that Doug started, and the proof that no one cares or knows about it is that the paper is about 10 years old, and I checked, and there's been one citation for it. So I'm hoping that I can get people interested in that stuff. So Adam pushed homology, as you saw in Haynes' lecture, where when you look at the Adams-Novikov spectral sequence, you want to use homology instead of cohomology. But when it comes to looking at spaces, I think that stunted our development. So almost nothing is known about the BP homology of a space, except for easy complex orientable stuff. With Dave Johnson, we have the BP homology of elementary P groups. And it's a really pretty answer. But to even go with a P squared, to stick a P squared in one of these places, or even just to do two groups and try to do P to the N and P to the M, it already gets incredibly hard. Yan has a nice description of the BP homology of BOQ. But it's hard to come up with other examples. Somebody will find something, but I don't know many more. So Doug and Nowacki and I switched to cohomology, and we get the following theorem. If the Morava K theory is even degree for all n, then the BP cohomology is Landweber flat and even degree. So in some sense, we know a lot about it just from that. And your first statement would be, well, yeah, but how many spaces have even degree homology for all Morava K theories? Well, it turns out that everything you can calculate has that property. So lots of spaces have even degree Morava K theory. Eilenberg-MacLane spaces, loops on finite Postnikov systems, the even spaces in the omega spectrum for the sphere, BON, the spaces in the even spaces in the connected complex K theory, all kinds of things like that. So this happens all over the place. But we should have paid attention a lot earlier and switched to cohomology instead of homology, because Landweber knew decades before this the BP cohomology of all finite abelian groups. He had written it all down, and it all worked. It was before Landweber flat, but it worked because he had Landweber flat. So that's the Ravenel portion of the lecture. I've known Doug for a long time now. It's coming on 50 years next year. And I've always known he was smart. In fact, to this day, when I come across a math problem I can't solve, I ask myself, how would Doug think about this? It doesn't work, because I don't have the slightest idea how Doug would think about it. But when the proof of the covariant conjecture stuff came out, that's really one of the nicest theorems in my lifetime. And it was really exciting, and it was no surprise to me that Doug was one of the authors. In fact, it was just completely appropriate from my point of view. And you know how it is when you prove a nice theorem and you feel really good, and you go out and celebrate, and then you come back and you find the mistake and you fix it, and then you celebrate again, and you come back. And this is how we have a good time in mathematics, right? And eventually you prove it, and you got to stop celebrating and go do something else. But there's that really good feeling when you prove a theorem. And when I had heard that Doug was involved in this, I felt that way even more so on behalf of Doug. I just thought that was fabulous. So anyway, happy birthday, and thanks for all the fun. Okay, it's also the part where I'm done now with the BP and Morava-K theory. I want to talk about current stuff. It's, we call these ENs. They're periodic, and they have an action of complex conjugation. Hu and Chris studied the fixed points of these. They got new theories, the real Johnson-Wilson theories, and showed that they computed the coefficient ring in what has to be one of the ugliest descriptions of something that, well, it turns out it's really ugly. So it's not unreasonable to have an ugly description of it, but you can do better than they did. And they showed that it was periodic, and there's the periodicity. It's 2 to the n plus 1 times the periodicity of En. And developing these ERNs is a process that's very much like that happened 50 years ago with BP and Morava-K theory. First, we actually have to study the theory to be able to use it, and then we have to have applications. So this work is joint with Neetu and also with Vitali. So here's a survey of our work so far in this area. The foundation is that if you look at the fixed points and you look at the inclusion, the fiber of this is really simple. It's just another copy of ERN. And now that means that you apply cohomology here, you get an exact couple. You start off, if you know the En cohomology, then you have a spectral sequence that goes for the ERN one. And if you look at that map, then it turns out that it's 2 times it is 0, and it has finite order. And finite order means that the number of differentials in this Box-Stein spectral sequence is finite. The very first case is just real K theory and complex K theory in their relationship. KO is 8 periodic, and KU is 2 periodic, so it's 4 times that. And here's the exact sequence that you get there, and you have the usual X has a different name, but X to the 3 is 0. We do some stuff in our development for arbitrary N, but we often do it just for N equals 2. There, it's 17 suspensions, and X to the 7th is 0. So there's only 7 possible differentials. We've never actually seen an even differential, a D2, D4, or D6, and we've only seen a few D5s. So ER2 is 48 periodic, E2 is 6 periodic. And let's start back in the beginning. For BP, we looked at the homology of these spaces, and now that was where we looked first with these things. You have the omega spectrum. It's some big periodic thing, and you'd like to know something about the homology. And we have various results, but here's one. If you go back, it was Mike talked about it. If you looked at MU and you looked at the real MU and the fixed points there that Araki and Landweber studied a long time ago, if you look at the BP analog there and you look at the 0 space in the omega spectrum, then the real version has the homology, looks exactly like it. You just divide the degrees by 2. All the coefficients are mod 2. So we actually know the homology of the 0 space in the omega spectrum for the real BP. We don't get all of the spaces for ERN. There's a lot of them because it's periodic, so there's that many spaces. And these spaces are special. They're special because we can actually calculate them. That's the definition of special. It doesn't look like that's what we get here because there's a certain amount of twisting around. You know, this number doesn't look like that number. But again, we just have the I and the 2I here. And we know all of this stuff. That the homology there is well known. But you've seen things like this happen before. If you look at the homology of BO, it's just, I say it's half of BU, but apparently the technical term is it's the double. So it's double BU. For n equals 2, the periodicity is 48, and that theorem that I showed you gives us the spaces 0, 16, and 32. So there's a lot missing there. But in general, we know 2 to the n minus 1 spaces, which does not cover all of the spaces in the omega spectra because of the periodicity. It's much bigger than that. A little bit about how to do that. If you look at BU, and you look at the image of CP infinity, the homology of BU is just a polynomial on that image. Now, if you take the fixed points of all of that, it's a polynomial. BO is a polynomial algebra on the image of RP infinity. So we had to generalize this. We have equivariant maps of smash products of CP infinity, lots of these things. And if they generate, then this is a really nice space that we can do stuff with. And MU and ERNs all fall into that category. We go further. Neetu and I, we did all 48 spaces. You could ask why, and that was certainly a question uppermost on our mind when we finished. But there's a reason for it. We actually were looking for something because if you look at ER1, that's just BO, and there's 8 spaces. And 5 of those 8 spaces have no torsion. BO is the ugly one, which we don't tend to think of it as the ugly one, but in the omega spectrum for BO, it's the ugly one. So we had all the ingredients necessary. We had an ugly one. And we thought we would start with there and go find nice ones by looking at all of the other spaces. And I'm still convinced that that's true. We just haven't figured out the definition of nice yet. And then we don't know how to prove that it's nice once we have the definition. But at any rate, we have all 48 of them. And they're not as bad as they might seem because everything in it, in this Hopf ring, comes from, just like all the other Hopf rings you've seen, come from RP infinity, the coefficient ring, and suspension. So you could, again, get a free thing on some relations. But we just don't know how to define free. That's we admit. Next, we have applications. You have to have applications. We have non-immersions, RPN. And if you look at ER2 of RP infinity, because this is the fixed point thing, you can actually calculate that. You have to adjust. For E2, you get a 2-dimensional generator, and it's a power series modulo the 2 series. Here you have to adjust the generator a little bit. That's why the little hat's there. And so that's easy. But to actually do finite spaces turns out to be hard. There are youth in the audience that claim they can do this as well, but I've given them a difficult problem. They have to prove that their answer is the same as our answer. And I think that might be the harder problem. So we compute this for all the even ones and one of the odd ones, and Romy does another odd one. And what makes it work is that if you look at this 2-dimensional class for E2, then the n plus first power has to be 0. But in the case, if you look at certain cases, our adjusted generator is in dimension minus 16, but it actually has one more power than it should have. And it has it in a very strong way. Some of the cases, there's even more powers. But this happens in a very strong way, in such a strong way that we can just piggyback off of Don Davis's calculations in his Annals paper where he gets all of his non-emergent theorems. And we can just say, it applies there, and we just get better theorems. And I think we get something like 1/8 of the known best non-emersions out of this. Our lowest one is RP48, does not immerse in R84. I urge all of you guys working with the big fancy machines to look at problems, real classic problems like this. There's no reason why we don't have a solution for this problem. And we don't even have a conjecture for it. So, and I mean, you have one problem, and you get to write a joint paper with Don Davis if you work on this, because if you prove a non-immersion, you'll have to go to him so he can prove that it's a new one. So we have the homology of ER2, and now we want the homotopy type. If you look at E2, if you look at the 0th space, it's BP bracket 2, 0, and an infinite number of copies of BU. It's 6 periodic, so if you take that, if you take this one space and you look at its 6th loop, you just get one of these. And that's why you have to have an infinite number of these, because if you want 6 periodicity for this thing, it's because infinity plus 1 is equal to infinity or something like that. And so Don Davis's theorem essentially uses E2. He doesn't use E2, but he really does. And if you go back, and these are the classifying spaces for this cohomology. And BU has been worked over for decades by the old guys, and so there's nothing new there. So if you're going to get anything new, it's out of these 3 spaces, because he only uses, it's 6 periodic, and he only uses the even ones. So if you look at, if you loop this down 48 times, because I want to be able to compare it with the 48 periodicity of ER2, you get 8 copies when you've done this. So we know that if you take ER2, the homotopy type, there is a space creatively called Y0, and we didn't even use a subscript. And there's an infinite number of copies of BO instead of BU. Now, when we do our calculations for non-immersions and lots of other things, we just look at the 16 multiples of 16 degrees. And if I do that, then you get the following theorems. If you loop down 16, you get a Y1, and you get 3 copies of BO. And you do that one 16 times, you get 2 copies, and you get a new space, and you loop that one 16, you get back to Y0, and you get 3 more copies here. And what do you get with that? You get, if you do it 48 times, that's the periodicity, you get back where you started, plus you get 8 copies of BO. So all of the new information for our non-immersions have to be in these 3 spaces. And we know the homology and the homotopy of these spaces. We know all that stuff about them. We have similar homotopy type theorems for all of the ERNs. It's just that I'm fond of ER2, so I told you about them. Before I go on to the next stage, since I think that in developing something, you need to be able to calculate the cohomology of spaces. But I want to talk about 2 quick things we've done before that. First, we show that there really is an adequate ring spectrum on these things. That was apparently a little up in the air. And then we show that if you take 2 to the n plus 1 times a bundle, it's ERN orientable. Now, that gave us a new approach to non-immersions using ER2, and that led us to our test case I think Vitali, it was at about RP 57 or something. That was the thing we were looking at. So we didn't even know it would work, but we got, actually we didn't get 11,138 equations. We had another 10,000, but they were all 0 equals 0. So these are the non-trivial equations, and those are the number of unknowns. That project is probably dead. But you know, when you have a project that's dying, you can either do it, you can get a counterexample or something like that. But if you just have to give up on something, you want it to be unambiguous. And I claim that helps us over that unambiguous hump that we think we're done. Anyway, I'll get out of chronological order here a little bit. I've already discussed ER2 of RPN. Vitali computed ERN of CP infinity. And that sort of sounds easy, but it's not, because these things are not complex orientable. And so even if you look at the n equals 1 case in KO, it took decades to get everything you wanted to know about KO CP infinity. It wasn't until about 10 years ago that Yamaguchi finally nailed the last formulas. So what Vitali did was really quite impressive. So we've moved on. We've done the CPNs. We've done the KZ mod 2 to the Q1s, and we've done products of CP infinity. We've done BUQ. Again, these things, if they were complex orientable, they would be trivial. Easy to do, but they're not complex orientable. So just using ER2 is a problem. Those were all done by brute force, just computations with the Bachstein spectral sequence. And we only have differentials 1, 3, 5, and 7. And it just takes a lot of work. But we do see some structure there. We don't see a lot. We get Pontryagin classes, or at least modified Pontryagin classes. And in the CPNs, just like with the RPNs, we get higher powers of the Pontryagin classes than are there for E2. And so we were hoping that we would get something on non-immersions out of that, but it didn't work out. So we have a lot more spaces. In particular, this simple one here, the BOQ. I got the little hats. I'll explain the little hats on the Chern classes, but it turns out that you have to, if you do the BOQ is generated by the Chern classes, or modified Connor-Floyd Chern classes, and the complex conjugate has to be equal to the Chern class because it's back on the reals. And so this relation is all it takes. So you have to modify these Chern classes just a little bit by multiplying by powers of Vn. But Vn's a unit. And this multiplication makes these things permanent cycles in the Bachstein spectral sequence. So you need to do that to get that. So when n equals 2, this puts the degrees of the Chern classes in minus 16k. Now, we knew this theorem for BOQ, but the proof is non-trivial. The proof is you actually do it with the atom spectral sequence. And it's one thing to get the Chern classes generate using the atom spectral sequence, and another thing to actually get the relation between the Chern classes and the complex conjugates of the Chern classes and show that that's all there is. They had to be there, but to show that that's all there is. You don't want to see that. Now, in the paper with Yagita and Doug, we actually do the BO in an elegant form, which means it was Doug's, and without having to go into all the detail of the calculation. So getting to ERN is also non-trivial, but I'm going to talk about that in a bit. We use these modified Chern classes, and we use Landweber flatness, and I'll talk about that, but I first want to state more theorems. We also know the integral Eilenberg-MacLane spaces, the odd integral Eilenberg plane spaces. The even finite ones, although mod 2 we can do them all. We can do BSO, B-spin, a few other things. And the answer, notice there's gaps here, okay? We don't do the even integral things, and we don't do the odd mod 2 to the q things. Now, that's what makes Vitali's calculation of CP infinity so important. That's the first case of something that we don't know that doesn't fall out of the big machinery that I'm going to talk about in a minute. And likewise, for the BZ mod 2 to the q, that's the first odd case there. And again, that doesn't fall out of the big machinery. So what we have here is the ERN cohomology of one of these nice spaces is the tensor product of the coefficient ring with this thing with the hats on it. Now, the little tinfoil hats are there so you can't see what's going on. That's why you wear tinfoil hats. But on the other hand, it does something, it does two other things for you. And that is that one of them is if you see the little hat, you know it isn't the thing without the little hat, right? But if you see a little hat on one of these things, you figure that it has to have something to do with the thing without the hat. And so if you knew enough about the thing without the hat, you could probably get the thing with the little tinfoil hat on it. That's why you do this sort of thing. So recall the answer. Now, but in here, except for the hats on the Chern classes, there's no hats. But that's not true. So let me show you where the hats are. There were no hats here because this was the easy case. So it's really here with the hats. The tinfoil hats are back. And if you look at the Bachstein spectral sequence that goes from En of x to ERN of x, it's as ERN star modules. But I want to use Landweber flatness, which I haven't told you what it is yet, but I'll get there. And you want it to be an En star module, not an ERN star module. So we have a map of ERN star to En, but we want to get a map of we want to make En star a module over En. And you may think that's simple because it's just En, but you want it to be a module for the whole spectral sequence, and it's an ERN star module. And so you have to have a map of En star to ERN. And we do that by taking the tinfoil hats back. The composition, we get a map of VK to a VK hat in ERN. And if you look at the composition now, it sends VK to this thing with a bunch of powers of Vn multiplied by it. And this VK with the hat on it is a permanent cycle in here because it's in here, right? I mean, so if it goes down here, but it comes from here, that makes it a permanent cycle. So the V hats are things that we like. And if you look at this map, it multiplies degrees by this, okay? Now, when we were graduate students and we were doing graded algebra stuff, that was not in fashion among non-algebraic topologists, and they looked down on it, but we had rules for graded algebras, and this is not one of the rules. And so it's a little disturbing to work with these, but you get used to it. But the image, it's injective. So the image in ERN star is the thing with the hat on it, but it's isomorphic to En star. Just the degrees are all screwed up. So this makes En star into an En star module in an exotic way. In particular, it's an E hat En star module. The VK are perfectly good replacements for VK because you're just multiplying by a unit, but that's not true for Vn. You're multiplying by a unit, but when you get down to En, you're not necessarily getting a generator. So if you look at En star as a module over E hat N star, it's free on a finite number of powers of Vn. because when you go to that Vn hat, it's really a bunch of powers of Vn, and so you're missing some. So in particular, you get this tensor product with the hats that gives you back En star from the versions with the hats on them. So in general, we always assume that the En cohomology of X is even degree, and we assume we know it. And we do know En cohomology for lots of spaces. And now we want to do the same thing. We want to hat all of this. And the way you hat it is you multiply by lots of powers of Vn. And that, because Vn is a unit, this is injective. And so we look at the image of it, and that's the hat. It's not a cohomology theory, but it's isomorphic, if you ignore grading, to the cohomology, En cohomology of Z. Now we have En cohomology of Z is, you can get it back from the hatted stuff by just tensoring with En star. So here's the easy one. With this theorem, this is the start of the Bochstein spectral sequence. You start with En cohomology of something. So what we really want is to ignore this thing. If this thing is known to be Landweber flat because it's isomorphic to the En cohomology, and furthermore, it's made up of these Chern classes, which are going to be they're all permanent cycles, and the V hats over here are permanent cycles. And so what we really want, we want all the differentials to be just on the coefficients, to go from En to ERN. So these are permanent cycles, Chern classes, and Landweber flat. Those are the ingredients that go into this. And if Landweber flat meant flat, then we'd be done. We could just do the differentials on En star. But because of that adjective, Landweber, it doesn't mean flat, so we have to talk about what it does mean. The original Landweber flat worked, it meant flat for a particular category of finitely presented, meaning over BP star, BP comodules. So you had to have a lot of structure on what you were looking at, and then it was flat with respect to that category. So that tells you now what Landweber flat really means, and it turns out that that criteria that I gave you in the beginning is true for all Landweber flat things, historically before Landweber flat evolved. So to make this work, we need this Bochstein spectral sequence from En star to ERN star to be in a good category that makes Landweber flat flat for it. Now, it's evolved, and we don't have to use BP star BP. We can use En star En. And we went to a lot of trouble first to make En star an En star module by taking En star, putting it in E hat, and then in ERN, and then to En. But we made it a module, and then we have a very nice, we need all of the pages of the spectral sequence to be in this category, and we need all of the differentials to be in that category, just for the coefficient ring. But we wrote down the Bochstein spectral sequence for this very carefully and very nicely so that you can just see that this is true. And once that's true, all of the differentials in this thing are now over there. They're where they're supposed to be. They're right here. You just do the differentials here, and that's the differentials for the spectral sequence, and you get this end result. Yes. So in the case of BO, these were just fixed points for BU, and so we could show that the CK were permanent cycles. That made things easy. Our other spaces are not so nice. We need to map our Z to an equivariant space X. This space has to have that previously discussed property about coming from equivariant things from CP infinity, getting generated. But this is not the space we're interested in. This is the space we map to. And then we have to know En star of Z, and we have to know its Landweber flat. So we have to know a lot of stuff, but there's a lot of things we know this stuff about. So the simple example that got us started in this stuff is just looking at KZ3. Okay? There's a map to BU6, the sixth space in the connected complex K theory. BU6 has no torsion. It has a complex conjugation. It has all these nice properties. We have this fibration, and it turns out that the En cohomology of KZ3, this is from the paper with Doug and Yagita, is just the quotient of this En cohomology of BU6 and BU4. Now, that's true actually for arbitrary integral Eilenberg-MacLane things. This BP bracket space, this coefficient down there at the bottom, is the biggest one that still has these things with no torsion. And if you deloop it one more time, you get torsion. And so you get this really nice thing, and we have no idea what the En cohomology of BU6 is because it's not complex oriented, and that's a really nice torsion-free space. But we can use this and the big machinery we set up to get ERN of the third integral Eilenberg-MacLane space from the En thing in the formula that I gave earlier, even though we don't know the stuff that we come from, even though we need all of that stuff in our machinery. So that was just the simplest example of that. Enough.